All right, hello everyone. So today we're going to be finding the cube roots of complex numbers. We've got 5 plus 5 root 3i. Okay, so essentially what we're looking for is numbers z in the complex plane, or just imaginary numbers, such that when you take these, take z to the third, it's equal to 5 plus 5 root 3i. Okay, that's what we mean by when we say something is a cube root of something. That means you raise it to the third power and it gives you the number that's being asked for. If it was fourth root or square roots, then it'd be raised to like the fourth, the second power, etc. All right. Now for this problem, we're going to make use of something called DeMoivre's theorem. And DeMoivre's theorem says something along the lines of, if you have a number z equals r times the quantity cosine theta plus I sine theta. So we're going to look at the numbers, writing them in polar form. Okay. Then if you take that number and you raise it to the nth power, here the nth power, I'm just going to work with positives today, says that number to the nth power equals r to the nth power times cosine of n times theta plus sine of n theta. So n is, you're going to multiply the angle theta times n, etc. And there's also another form of this, an equivalent and exponential form, which you can take a look at. So in our case, if we're looking for a solution, and let's say our solution is of the form z equals r cosine theta plus I sine theta, it's this right here. Yeah, if it's a solution to your equation up here, then if you would plug that solution into that z cubed, and that would come out to be r to the third times the cosine of 3 theta plus I sine of 3 theta. Okay, so again, we're assuming the solution, right, it looks like this in polar form. And if we say it's a solution, that means that if you raise that to the third power, you get this right here, but that has to equal all of that. Now, the issue for us now is, that's great, but that number, the 5 plus 5 root 3i, I want to write it in polar form, because my left-hand side, where I have, again, the 3 and, the r to the third cosine 3 theta plus sine 3 theta, again, this side right here, yeah, that's in polar form. So I'm going to do the same thing. I'm going to rewrite that in polar form, and that's equal to 10 times the cosine of pi over 3 plus I sine of pi over 3. Now, you might ask yourself, how did I do that? R is equal to the square of each of the components, the real part and the imaginary. So 5 squared plus 5 root 3 squared is 25 plus 75. So let me focus in on that, which is 100. Square root of 100 is 10, so that's what your R is. And then we have that the tangent of your angle is equal to the imaginary component over the real component, which is square root of 3. And your angle that you're looking for is in quadrant 1. Now, how do you know that? Because we don't show this, but we're technically drawing out the complex plane here. And if you looked at your angle that you form, the x is 5 units and 5 root 3 for the y here. So that's how we get the tangent of angle is root 3, and it's in quadrant 1 here, okay, because both 5 and 5 root 3 are positive. So that's very important that you know where the quadrant is at. And anyways, I'm asking for which angle in the first quadrant has the tangent of root 3. Well, that's got to be pi over 3, so it's a matter of looking at your unit circle. So what I did next was as follows on this line. I took what my solutions would look like, and I set it equal to this now written in polar form, the 5 plus 5 root 3i. So that's equal to 10 times the cosine of pi over 3 plus I sine of pi over 3. And how would I go about, solving for r and theta? That's what you need here. R cubed would imply 10, because if you set things equal to each other, then this equals that. And the angle right here could equal pi over 3. And if that was the case, then 3 theta would equal pi over 3, or theta is pi over 9. Okay. Now I said could be. There are more solutions to this. we need to find more solutions because we need 3. When we find the cube roots, that means there's 3 roots here, 1. And also, when you have a complex equation, like z to the third equals an imaginary number, or whatever, you have to have that number of solutions it's called the fundamental theorem of algebra. So you need to look for the other 2 here. Okay. Now, how do I find those? Well, we use the fact that if you add any multiple of 2 pi to an answer, okay, this will also be an answer. So if you take pi over 3 and added 2 pi k to that, that would be an answer. And if you set the inside to it and you solve for theta, you would get pi over 9 plus 2 pi k3. So again, if you add 2 pi k to any angle, we're going to go ahead and find a solution to your answer because of the fact that sine and cosine have a period of 2 pi. And the inside would have to be pretty much pi over 3 plus 2 pi k. Well, if you solve for theta in that case, you still get your pi over 9, and you get 2 pi k over 3. And how would I get the solutions? If you plug in k equals 0, 1, and 2 in there. You plug 0 in, you just get pi over 9 again, so that's the first solution we got. If you plugged in 1 and you did some math, again, plug 1 into right here, you would have pi over 9 plus 2 pi over 3. You would get 7 pi over 9, and then if you plug 2 in, you would get pi over 9 plus, so k equals 1, k equals 2, would equal pi over 9 plus 4 pi over 3, which is 13 pi over 9. Now, yeah, you might say, well, you can go on and put more k's. The issue with when you try k to be 3 now, you would get pi over 9 plus 2 pi. But see, you already have accounted this solution for pi over 9 because the sine and the cosine of 2, say, coterminal angles are the same. Okay, coterminal angle means that the angles lie in the same position, which, yeah, if you add 2 pi to any angle, that's what happens. So no k over 2 here is necessary as I have here. So it's k equals 0, 1, and 2. So what we're going to do here is we're going to get our r that was equal to the cube root of 10 and your angles and plug them back into the polar form for an equation. Okay, so this is what this would look like. These would be your solutions. And obviously, if you want, you can use a calculator to approximate what each of these are, the cosines, and the sines, and distribute the cube root of 10. Now, you know, you might say this method's okay, but I like something a little more formal to this instead of me just kind of using these facts here, which I understand. And yeah, we do have something in a general formula here, which says if you're looking for the nth roots of an imaginary number, and that imaginary number is, you can write it as r times cosine theta sub 0 plus I sine theta sub 0. The solutions are given by this formula. So k equals 0, 1, 2, all the way up to one value less than the roots that you're looking for of that equation. So in our case, we were looking for the third root, so it'd be the cube root of my 10 times the cosine of theta sub 0 is where the angle is of the solution given, so that was pi over 3 plus 2 pi k all over 3 plus I sine of theta sub 0 plus 2 pi k over 3. Oops, I'm sorry. It should be pi over 3. So again, the r comes from you rewriting the number that you're looking for the root of in terms of in polar form. So r would equal the square root of the component squared, added together, and then you find the angle in that similar manner when I went over the tangent, looked at the quadrant. So this is what your equations would look like for your solutions. And if you simplify this, this becomes cube root of 10 cosine of pi over 9 plus 2 pi k over 3 plus I sine of pi over 9 plus 2 pi k over 3. And you plug in the solutions k equals 0, sorry, the value 0, 1, and 2 in there. and you would get exactly the same thing we got over here for our solutions. So this method down here is a lot more standardized in my way, more mechanical. But some people just don't like it because you have to remember a formula, which is not easy to remember. And it's a little awkward in general when they're playing around with it. All right, well, I hope this helped. Thank you for your time.